So the problem statement is a lossless air dielectric open circuited transmission line of characteristic impedance Z naught is equals to 15 ohm and length L is equals to 6 meters is initially charged to V naught is equals to 21 volts. The switch is closed at time t is equals to 0. Determine the voltage across the load if ZL is equals to 20 ohms. How do we do this? Let's first find out how much time does it take for the signal to traverse the transmission line. Okay, so we know that that time is given by L by U. Now in this problem we are not given what the velocity is. So because it says it's a lossless air dielectric open circuited transmission line of characteristic impedance Z naught is equals to 15 ohms. So we are assuming that the wave traverses through the air dielectric, which basically has a speed which is equivalent to c. Okay, so we know that the length of the wire is 6 meters divided by 3 into 10 to the power 8 meters per second, which gives us about 20 nanoseconds as the time. Okay, so t is equal to 20 nanoseconds is the time it takes for a signal to traverse from one end to the other end. Now we're given that the initial voltage V naught is equals to 21 volts. Okay, V naught is equals to 21 volts. Let's also in the meantime calculate what the gamma L would be if uh, uh, RL was connected to the circuit. Okay, so gamma L would then be ZL minus Z naught divided by ZL plus Z naught. This is only after t is greater than 0. Or the better way would be to call it as t is equals to 0 plus. Okay, this is true only then. Otherwise gamma L is equals to 1 because ZL is equals to infinity. T is equals to 0 minus. Okay, so that is going to be we know that Z load is 20 ohms. We know that Z naught is 15 ohms. So divide by 20 plus 15, that is equals to 5 divided by 35, that is equals to 1 by 7. Therefore gamma L is equals to 1 by 7. Okay, so we have found out what gamma L is. We have found out what time period t is. uh, all that we are left is to find out uh, what happens to the voltage. Now let's just look at uh, a bounce diagram and try to put together things from stuff that we already know. Let's assume there was a voltage. If this is the source side, or if this is the side where uh, if this is how our circuit is, okay, if this is how our circuit looks like, so this is Z is equals to 0, this is Z is equals to L, this is our load. Let's assume we start off with some voltage. We don't know what that is, but let's assume this is the voltage. Okay, now before the load is connected, the gamma L on the right hand side is actually equals to 1. You can calculate gamma L with ZL is equals to infinity, and you will find that gamma L is equals to 1. And then, which means all the voltage that comes here gets reflected back to the source side. Okay, now again on the source side, because there is no load of any sort, because it's open, again all of it will get reflected back to the load side. Okay, now let's assume this is where the switch closes. Okay, so let's call this is equals to t is equals to 0 on the bounce diagram. Now before we draw any conclusion, let's see what happens to gamma L. Let's see what happens to the voltage on the load side. So we have said that this is equals to V naught, okay, before t is equals to 0. Its initial charge is V naught. Now we know that before t is equals to 0, we know that the total voltage is the sum of this plus this. Now here there is no any absorption of any sort because it reflects all the way. So if a voltage x came here and reflected back in this direction, the total voltage should be equals to V naught, but we know that anything that came here went all the way back. So the only way this will add up is when the voltage uh, on each of these was V naught by 2 and V naught by 2. So if this was V naught by 2 and this was V naught by 2, the one which goes in the forward direction here will basically reflect back entirely towards the source, and the voltage at the load would then be equal to V naught. Okay, so here is how we know with the voltage, the individual parts of the voltage should have been V naught by 2. Now, once we know that, we will go to the source side, and again here we have uh, lambda g is equals to 1 because again there is no load on the source side, so all of it will get reflected back, so we will have V naught by 2 here again. But at t is equals to 0, the switch will be closed, and as a consequence we will have a new gamma L which is equals to 1 by 7. So the next time what will happen is we will have V naught by 2 into gamma as the voltage going out. Okay, and again we will have the entire signal reflect back to the source side because this is always gamma g is equals to 1 here, so it's going to be gamma V naught by 2, and here again it will be reflected back uh, as we know with gamma square V naught by 2. Okay, so let's see what happens here. So this is t is equals to 0 nanoseconds, and then uh, this is equals to 20 nanoseconds, and this is equals to 40 nanoseconds, then this is equals to 60 nanoseconds. Okay, we are required to find what happens to uh, the voltage across the load uh, between 0 to t less than 60 nanoseconds. Okay, so we have done that. We will have to just find out what is happening at this point. Okay, so then the same voltage will get reflected back here. Okay, so 20, 40, 60. So on the load side, then therefore you'll have at time t is equals to 0 plus, you will have a voltage of uh, V naught plus, at time t is equals to 0, you will have a V naught by 2, which is the incoming voltage here, and a gamma V naught by 2, which is the outgoing voltage here. Okay, so that is going to make it V naught by 2 into 1 plus gamma. So we know that V naught is 21 divided by 2, 1 plus 1 by 7. So that is going to be 21 by 2 into 8 by 7. 7 3s are, 2 4s are, that's equals to 12 volts. So at t is equals to 0 plus, VR is equals to 12 volts. The voltage at the load side is going to be 12 volts. Okay, now what happens, so let's draw this out here in the even before we draw, let's just go further and calculate all the voltages. At t is equals to, let's say, it is going to remain the same way until 40 nanoseconds, but at t is equals to 40 nanoseconds, we will have VRL is going to be equal to 12 volts plus 12 volts plus gamma V naught 2 gamma 1 by 7 21 by 2, that is this one, and plus this one. Okay, that is going to be 1 by 7 square into 21 by 2. Okay, so that is going to give us 12 plus 1.5 plus 3 1.5 by 7. Okay, so that is going to be equal to 12 plus 1.5 plus 1.5 divided by 7 is equals to 13.714 volts. Okay, and finally at t is equals to 60 nanoseconds, VRL is going to be 13.714 volts plus at 60 nanoseconds it is going to remain the same thing. Okay, so we don't really have to change anything. It's going to be the same value. Let's just go ahead and find for 80 nanoseconds. Then VRL is going to be 13.714 volts plus uh, uh, 13.7 volts plus 1 by 7 square into 21 by 2 plus 1 by 7 cube into 21 by 2. That is the last one here. This is going to add up and give us gamma cube V0 by 2. This is at 80 nanoseconds. So the way it is going to look is going to be, it's going to add up to 13.95 volts. Okay, so this is the voltage at 80 nanoseconds. Now let's go ahead and plot these values. Okay, now we said at t is equals to 0, we are going to have a voltage of 12 volts. Okay, let's call this 3, 6, 9, 12, 15. So at t is equals to 0, we are going to have t is equal to 0, we're going to have 12 volts, and up until 40 nanoseconds, it's going to remain the same way. So if this is 20, 40, 60, 80, 100, 120, okay? It's going to be 12 volts up until 40 nanoseconds, and after 40 nanoseconds, it's going to jump to 13.714, so which is somewhere around here. It's going to jump to until 80 nanoseconds, and after 80 nanoseconds it's going to jump to 13.95, a further small jump. So this is how the voltage is going to look initially. Okay.